We are practicing free response questions using the 2013 free response questions from the AB calculus exam. So here is our question about the relationship between f prime, and f double prime. Read very carefully again. This is given to be the graph of f prime, and we are told that it is twice differentiable. So we know that f has a continuous first derivative and a continuous second derivative. So it's nicely behaved. We've got an interval from 0 to 8, a closed interval. They tell us that f prime has horizontal tangent lines at 1, 3, and 5, which is just to explain the graph. That's how it appears when we look at the graph. And we are told that the function f is defined for all real numbers and that it satisfies f of 8 equals 4. Well, make no mistake about this. This point is f prime of 8 is given to be 5. This is completely something different. F of 8 is on a completely different graph. So on the original function, we know the y-coordinate at 8 is equal to 4. And of all of the antiderivatives, that one point, that one initial point anchors. So we know exactly which of the antiderivatives we would keep. And it's going to be essential here as we evaluate some integrals. So in question A, we are to find all of the values of x between 0 and 8 that produce a local minimum. Well, there's our first derivative test. And I only see one place where the first derivative changes from negative to positive. So we could say that f has its only local minimum on the interval from 0 to 8 at x equals 6, since f prime changes from negative to positive. Or you could mention the first derivative test, but that's just as much writing. All right, and then in part B, determine the absolute minimum on the closed interval. So remember now that we have to add the possibility that the absolute extrema can occur at the midpoints. So the absolute minimum can occur at critical numbers or closed endpoints. Let me try writing can occur at. But now, do we really need to test all of the critical numbers? Well, there's two more of them here where f prime is equal to 0. But those we've already in part A ruled out that they do not produce a minimum. So we don't really need to test them. But you might just include them out of habit. Absolute minimum can occur at critical numbers or closed endpoints. So perhaps you might start a table. We're looking for the smallest y-coordinate on f of x. So you might say, well, it also has critical numbers at 1, 4, and 6, and its closed endpoints at 0 and 8. But you might say, well, I don't really need to test these values because they cannot produce a minimum. And then you could say C part A, since you've already canceled them out of the running for a local minimum. If they're not a local minimum, they certainly can't be an absolute minimum. Or you could just go ahead and find their y-coordinates, but that's going to take a little bit of effort. So let's think about this now. How are we going to find out? What is f of 0? Well, we don't have a graph of f. We have a graph of f prime. So what we do know is that if we integrate, that's an antiderivative, we should be able to get back to f. So if we take the only point that we know on function f is f of 8 is equal to 4. So if we started with the value of f of 8, and then what if we took away all of the area before that? So that would be the same as adding an area going backwards from 8 to 0. So I don't think I would have written it this way first. I think I would write it this way right away. If we subtract the area from 0 to 8. So if we subtract the area from 0 to 8 away from 4, that will get us back to the coordinate. So then we would come up with a negative 8 for f of 0. So we can fill it in the chart. And then we need to do the same idea for f of 6. We only know f of 8, but if we could either add on the area going backwards from 8 to 6, which is exactly the same as subtracting the area if we reverse the limits. And how do we know that area? It was given to us. So again, go back up to your picture and look at the region from 6 to 8. That region was given to be a 7. So that's why those areas were given. So f of 8 was 4, and we are taking away 7. So this value would be a negative 3. And f of 8, we don't have to do that work. Remember, it was given. F of 8 was given to be the 4. So now we can look at our contenders and come up with our conclusion. So our absolute minimum, f has an absolute minimum of negative 8 at x equals 0 on the closed interval from 0 to 8. And I think I have answered the question there. All right, let's press on. So that might be something you'll want to come back and practice if you haven't seen one like that before, because that's going to be a common question. Part C, on what open intervals contained between 0 and 8 will f be both concave down and increasing? Well, that's not too difficult because we know that f will be concave down when f prime is decreasing, and f will be increasing whenever f is positive. So can you find the sections on the graph? We're looking for the place where f prime is decreasing and f prime is positive. So do we see that there are two intervals where that's going to happen? So it's a matter of getting our justification correct here for part C. And you could write this in a couple sentences. Let's see if we can combine it. F is concave down and increasing. Those two intervals were from 0 to 1. Don't include the endpoints. There's no concavity there. And the interval from 3 to 4, since f prime is decreasing and positive. You could say and f prime of x greater than 0 if you wish. All right. And then letter D. Letter D says function g, a brand new function, is defined to be equal to function f of x cubed. And we've got an initial value. F of 3 is equal to negative 5/2. Find the slope of the line tangent to the graph of g at x equals 3. Well, a tangent line is, the slope of a tangent line is just the derivative. So we are being asked to find g prime of 3. Find the derivative of g. So that is going to require a chain rule. So we're doing the derivative of function g, and then we're going to plug in the 2 points that we know. Remember, we'll be able to get f prime from this diagram. So from the graph, we can read f primes. And here f of 3 is going to be a point we're clearly going to need to substitute in there. So let's find our derivative first. So g prime of x, do our power rule on the outside. So this is now squared, and then our chain rule, f prime of x. And now let's find out that value at 3. So if you just organize your work here so that you can read. So f prime of 3, we're going to get from the diagram. So let's scroll back up here. F prime of 3 is 4. And then the other value was given. So this value we get from the table. This value was given to us in the problem as -5/2. The values are chosen to make your life easier. When you square, this denominator will be 4, so it will cancel with that 4. So we'll have a 3 times 25 will be 75. And we're done.